The focus for our video today is in class 10. This is the part of standard 3. We're going to be focusing on two special types of triangles today. Isosceles and equilateral triangles are the main focus. So there is an introduction section. So thinking back to yesterday's notes, our goal is to classify each of the triangles that we've been given by angles. So go ahead and pause the video, give that a try. Meet me back here once you have answers, and we will see how you did. Welcome back. Remember, when we're classifying by angles, we have 4 choices. A triangle can be acute, equiangular, right, or obtuse. So when we investigate the first triangle scenario, the goal would be to find that missing angle, the measure of angle D. We can do that using the triangle sum theorem. All 3 interior angles have to add to 180. So that turns out to be 118 degrees, which is more than 90, so that would be an obtuse triangle. For example 2, they're showing us that all of the angles match. They're all x, which means they're all equal. If we were to solve, we could take 180 and divide it by 3 to figure out that x is equal to 60 degrees. That means our triangle is equiangular because they're all the same. For example 3, we see a right angle marked with that box. We don't know anything about the other angles, but that's okay. As soon as we see one right angle, that means we have a right triangle. And last but not least, we've got a little algebra equation to solve for this last one. The angles are all 3 mysteries, but we know since they're on the inside of a triangle, they have to add to be 180. Once we track down x, we can plug that back in to find the individual angle measures. And since all 3 measures are less than 90, that would be an acute triangle. So some vocabulary review from yesterday. Moving into the new material, we're going to look at what happens when a triangle has some congruent parts. As a reminder, the word congruent could be symbolized with an equal sign with a squiggle on the top, and that means that things are the same size and the same shape. So when we look at this first example, it says that this is an isosceles triangle, and what we notice is marked as congruent would be side EF and side FG. Those 2 segments are marked with ticks, and so we know they're congruent to each other. If we look at example B, that's an equilateral triangle, our second new vocabulary word for today, and we notice that all 3 of the sides of this triangle are marked with those ticks. So all 3 of them are congruent and have exactly the same measure. We've already talked about equiangular a little bit, so this third example is showing us an equiangular triangle. That's showing us that all 3 of these angles are equal to each other, all congruent. And so what happens with triangles is that equal sides are going to give us information actually about equal angles as well. If we travel across the triangle from a congruent side, we're going to make our way to what we call the opposite angle. And if these 2 sides are congruent, then when we travel to these 2 opposite angles, they will also be congruent. So when sides have the same size, the angles across from them have the same size. So if we do the same thing with our equilateral triangle, we're going to travel across from all 3 sides, which means we're going to end up with all 3 angles as being congruent. And then on the flip side, if we start with the angles congruent, we can travel across to the opposite side and mark that those sides are going to match as well. So when we have congruent information in a triangle, it's kind of like a 2-for-1 situation. If we have congruent angles, we can find some congruent sides. If we have some congruent sides, we can find some congruent angles. And those are the ideas that are going to help us to solve problems. So if we move to the next section, important vocabulary and theorems, we're going to kind of formalize those ideas, sorry for the slantiness there, and give them some names. So the first idea that we're going to talk about in terms of formalizing what we just did up above is the base angle theorem. The base angle theorem tells us that if a triangle is isosceles, In other words, it has these two congruent sides. Then the angles opposite the congruent sides are also congruent. So this is the isosceles fact that we start with. And then what we end up with is not only the isosceles fact marked, the two congruent sides, but also if we travel across, we're going to get to two angles that have matching measurements as well. The next idea is called the converse of the base angles theorem, which just means that we flip the two parts of that sentence. So we're going to start with a triangle that has two congruent angles. We can see that pictured right here. So we start with those angles. And then what we're able to say as a result is that the sides opposite those angles are congruent. So we'll start at this angle and travel across. That would take us to this side. Then we'll start at this angle and travel across, and that would take us to that side. So that idea works in both ways. If we start with the sides, we can find some congruent angles. If we start with some congruent angles, we can find some congruent sides. And then we have what's called a corollary of the base angles theorem. That's an idea that's related to the base angles theorem. This related idea starts by showing us three sides that match. So we called that earlier today equilateral. That was one of our new vocabulary words up top in our ABC examples. So if a triangle is equilateral, then we know that we can travel across from those congruent sides and make it to three congruent angles. And we had a word yesterday for a triangle that has three congruent angles. We called it equiangular. So basically, if we have an equilateral triangle, then we also know we have an equiangular triangle. If we flip that idea backwards and talk about the converse of that corollary, if we start with the angle information, that means we start by knowing that a triangle is equiangular. Then we're going to be able to mark those congruent sides opposite of each angle, and we will also be able to classify it as being equilateral. Now, we're not going to ask you to memorize the names of these things quite yet. Some of them will show up in a later standard when we start doing proofs, but for right now, the idea is that you need to understand them and solve problems with them. So don't worry too much about memorizing those phrases right now. Focus on the ideas and what's true. All right, the second phase of today is to continue our classifying. So yesterday, or in our previous notes, we classified triangles based on angles. Today, we're adding some more vocabulary words that will help us classify triangles based on sides. And we've already used two of these vocabulary words today. So isosceles and equilateral have already popped up. Isosceles was a triangle with two congruent sides, and equilateral was a triangle with three or all congruent sides. Scalene is the new one, and that's going to be a triangle that has no or zero congruent sides. So basically, all three sides are unique. They're all different. So they're asking us to go back now to the beginning in the introduction section and classify the triangles up there based on their sides if we have enough information to do so. So if we go back to these examples at the top, we're going to need to look carefully because all we have are angle clues. But when I investigate the angles in this first triangle, I'm noticing there are two angles that match. So if we use our converse of base angles theorem down below, that means that the sides opposite those angles, so DF and then DE, would also need to match. So that obtuse triangle could also be classified as an isosceles triangle if we were classifying based on sides. For example 2, all three of our angles matched. So now we know that that forces all three of our sides to match as well. So it's equiangular when we talk about classifying based on angles, and it would be equilateral when we talk about classifying based on sides. Number 3 is tricky. We only know one angle of this triangle, so we do not have enough information to classify this one based on sides because we don't know if these other angles match or if they're different. If these match and both are 45 degrees, then this would be an isosceles triangle. But if these are different, then all 3 sides would be different and we would call it scalene. So that one we're not able to classify based on sides. We don't have enough information. But example 4, last example, all 3 angles are different. That means that all 3 sides are also different. So this one would be an example, the first one we've seen so far today, of a scalene triangle, where all 3 sides have their own unique measurements.